So dilations are when we take its shape, the original shape, and we enlarge it. You enlarge every single side. So every vertice of a triangle will be moved the same distance. So let's look at the three triangles given to us. From A up to A prime here, these two triangles, the black triangle and the blue triangle, are the exact same size. So it was not bigger, it is not smaller. Because you can also dilate to make an object smaller. Therefore, since it's the exact same size, that is not a dilation. Here, if you look from A to A prime, and B to B prime, C to C prime, the blue triangle looks noticeably larger than the black triangle. This is a dilation. This is called an enlargement, where the shape gets larger. So you took your original, which is the black triangle, you enlarged it to get the blue triangle. Now, every single side is enlarged. That's important to know, because when we go over to this third graph, side BC is 3 units long. Side B prime C prime is 4 units long. That could be an enlargement, but if you look at side AB, which is 2, A prime B prime gets smaller at 1. So you cannot make one side larger and the other side smaller. Everything has to be proportional. The sides are proportional. You have your coordinates are proportional. Everything is done the same in a dilation. So looking at these graphs, which would be a dilation, this image is the same size as the original, so that is not a dilation. Here, this side is the exact same size as its corresponding side, but A prime B prime got bigger than AB, so we're doing different things with different sides. Remember, we're doing the exact same with every single side of the triangle. So that means that this third one here is an enlargement, which is a dilation, a form of a dilation. So there's two types of dilations. There is an enlargement. That's when an image is larger than the original. Each vertice in the original shape is multiplied by what we call a scale factor, and that scale factor is greater than 1. So any number greater than 1 is going to be an enlargement. A reduction is when we make a shape or an image smaller than the original shape. So each vertice of the original shape would be multiplied by a scale factor or a number that is less than 1. So 1/2, 3/4, things like that. So let's get into it. This first graph right here would be an enlargement. We are making the original, the black shape, larger into the blue shape. And to find the scale factor, you can count the side lengths. So in the blue shape, from point D prime to point C prime, that is 9 units long. That's where I got the 9 from. And then you do the original shape, its corresponding side. So we did D prime to C prime. So the original would be D to C, which is 3 units long. So that's how we got the 3. It is always the length of the image divided by the length of the original. That's how we find the scale factor. So 9 divided by 3 is just 3. So that's how we get a scale factor of 3. So here we go again. The length of the image, which is this small side right here. So this shape is getting smaller. The original is the black. The image is the blue. So we're getting smaller. So the image, the length of D prime C prime of the image is 3. The length of DC of the original is 9. 3 divided by 9, or 3/9, reduces to 1/3, and that's how you get the scale factor of 1/3. So let's find the scale factor of this dilation. First of all, the original PQRS is the black rectangle. The blue rectangle is the image, and the blue one is larger than the black one. So this is going to be an enlargement, meaning my scale factor will be greater than 1. So you can pick any two sides here. I picked to go with P prime to S prime, and its corresponding side would be P to S. So the length of P prime S prime is 6 units. The length from P to S is 3 units. 6 divided by 3 is 2. So my scale factor is 2, so the image is twice as big as the original. Again, you can pick any two corresponding sides. Here I picked L to M, so it's length of the image over length of the original. The image is smaller than the original, so we are going to reduce its size. So from L prime to M prime is 4 units in length. And from L to M is 8 units in length, which gives me a scale factor when I reduce that fraction of 1/2. So my reduction of the shape is 1/2. My scale factor is 1/2, meaning the image is half the size of the original. Now we're given vertices. We want to give it a scale factor of 3, so we're making it larger. We want to find the vertices of the image. So the original point A, the coordinate is 1, 2, which I have plotted. You should plot that as well. To find A prime, we take the scale factor and distribute it into our coordinate. 1 times 3 is 3. 3 times 2 is 6, so it's the point 3. 6 is A prime. We have to do the same with all of these. Distribute 3 to point B. 3 times negative 2 gives me negative 6. 3 times a positive 1 gives me 3. So that gives me the point for B prime is negative 6, 3. There is B prime. And last is C prime. So I take point C, negative 1, and I distribute my scale factor. And I get negative 3, negative 3. And there's my point C prime. You can connect these to make the triangle that is larger than the original. Here, if we read the directions, we just want the coordinates of M. That is it, or of M prime, sorry. So we only need to take the coordinates of M, 8, 4, and multiply it by the scale factor of 3/4. So if I distribute this to my point, 8 times 3/4 gives me 6. 4 times 3/4 gives me 3. So now my coordinates for M prime is 6, 3, and I can graph it. So there is M prime. Now I know 3/4 is less than 1, so if I were to do all the coordinates, I would know that it is a reduction, that my image will be smaller than my original.